Okay, honors chemistry people, we are going to start learning how to use those quantum numbers that we talked about last time. And we're going to start learning how to use them in terms of figuring out electronic configurations. We're going to use a hotel analogy proposed by Henry Eyring. Now, I told you a little bit about Henry Eyring last time. He was studying under Einstein at Princeton. In the early 1960s, he was brought here to Salt Lake City, and he was brought here to the University of Utah to start their graduate studies program. Little known fact, Henry Eyring was actually born in the Mormon colonies in Mexico. So he was actually not originally a United States citizen. He was actually from Mexico. And he came up from the Mormon colonies in Mexico when he was a young child and grew up in the Gilbert, Arizona area. So, in this analogy, he likened or he compared the way electrons go into the atoms to people going into a hotel. Now, in this analogy, each floor is an energy level. Each floor is like an N level. So our first floor, second floor, third floor, fifth floor, that's all going to be energy levels. And then on each floor, there are a certain number of halls. Now the hallways are our L quantum number. Okay, so this L quantum number is going to be our hallway number, however many halls. And along each hallway, there are a certain number of rooms. And our rooms are our M number or our M sub L number. Okay? And then each room has two beds, one for each electron, the upspin electron and then the downspin electron. So that is going to be our M sub S or our S number. Now, the thing that you have to remember about this hotel is it's kind of a weird hotel. Number one, there is no elevator. So when you go to that hotel, you are going to want to spend the least amount of energy that you can in order to go to your room. And since there's no elevator, you are going to go to the room that is closest to the ground floor. Okay? So you're going to want to go to the room that is closest to the ground floor. Meaning that you are going to want to keep your energy down. So we are going to keep the energy as low as possible with these electrons. The other thing that is strange about these electrons, but I really don't think it's super strange, is if there is a room or an orbital, remember the rooms are the orbitals. If there is a room or an orbital at the same energy level or in the same hallway, they are going to go into the room that is unoccupied. They don't want to share rooms unless they have to. So electrons will go into orbitals that are not shared. First, before sharing. Kind of like people. You'd probably rather have your own room than have to share a room at your hotel. Okay? So, now, both of these rules they're different expressions of rules that we are considering here. So the electron's going to the lowest energy room first, or the lowest energy orbital first. That is the Aufbau principle. Okay? Now, you'll notice that a lot of these have German words to them because guess what? The people that came up with quantum mechanics, they were German. So Aufbau, or the verb aufbauen, means to build from the ground up. So we are building from the lowest energy level on up. You can't build a building without building from the bottom up, okay? And then this second rule where the electrons are going to go into empty orbitals of the same energy level before they share, okay, or different orbitals before they share. This is called Hund's rule. Okay, so this is the map of the hotel, for lack of a better analogy. So notice as our energy goes up, we have our patterns of the orbitals that are going to be filled. So we have our 1s orbitals right here, 2s, 2p, 3p. It will come in handy to have this really quick. Okay? So the arrangement of electrons in an atom is called the atom's electron configuration. Because low energy systems are more stable than high energy, we are always going to keep things as low energy as possible. Electrons in atoms tend to assume the arrangement that gives them the lowest energy possible. The most stable, lowest energy arrangement of the electron is called the ground state configuration. 3 rules or principles: the Aufbau principle, where we go from the lowest energy up; the Pauli exclusion principle, where we cannot have electrons having the same spin in an orbital. Remember, we have to have an up spin and a down spin. And Hund's rule, where the electrons at the same energy level will go into single orbitals instead of sharing, define how electrons can be arranged. Okay? So Aufbau principle, once again, it states that each electron occupies the lowest energy orbital possible. So just think about it this way. That hotel has no elevator. You are going to go into the lowest floor or the lowest room possible. Therefore, your first step in determining an element's ground state is to learn the sequence of atomic orbitals from the lowest to the highest energy. This sequence, known as the Aufbau diagram, is shown in the figure above. And this figure right here is the Aufbau figure for the hotel. Okay? Okay? Hund's rule. The fact that negatively charged electrons repel each other, right? 2 negatives next to each other will repel each other, is important on the impact of the distribution of the electrons through equal energy orbitals. Hund's rule starts that single electrons with the same energy or with the same spin must occupy equal energy orbital before additional electrons with opposite spins can occupy the same orbitals. In other words, if I have a bunch of orbitals that are the same energy, the electrons are going to go into each of those same energy orbitals as single electrons before they start to share. For example, let the boxes below represent 2p orbitals. 1 electron enters each of the 3 2p orbitals before a second electron enters any of the orbitals. So we will go in sequence. We will have the first electron coming in here. The second will take the next orbital so it doesn't have to share. And the third electron will have the third orbital so that they don't share. Now, when that fourth electron comes in, they have to share. So they are going to start doubling up. And you will see that here. They don't double up until each of the orbitals at that energy level are completely occupied by a single electron. Okay? So, and when we get unpaired electrons like this, we get a really cool thing going on called paramagnetism. If you want to look that up and do some fun YouTube videos on that, it's a really cool phenomenon. Okay, So let's look at orbital diagrams and electron configurations. Okay, so here are the first orbital diagrams and electron configurations for the first 10 elements. Now we're going to do these one by one so that we can piece them together. I just wanted to have you have the examples of them. We're also, while we do this, we're going to put what's called electron dot structures. Now these electron dot structures are given to us by Gilbert and Lewis. This is our first American scientist that we're talking about. He was out at Stanford, actually. Brilliant guy. And we use Lewis structures a lot in chemistry. And we'll do a whole bunch of Lewis structures coming up in the next couple weeks. In biochemistry and organic chemistry, Lewis structures that's pretty much what we do, okay? My whole life, well, not my whole life, but my last 2 years at my undergraduate at Brigham Young University, Lewis structures all the way, okay? Because valence electrons are involved in forming chemical bonds, chemists often visually represent them using a simple shorthand given to us by an electron dot structure. This was proposed by Gilbert Lewis. Okay, and an atom's electron dot structure consists of the element symbol, which represents the atomic nucleus, and the inner level electrons surrounded by the dots in the valence. Okay, and the valence electrons, valence just is a fancy word to say the outer shell electrons. Okay, so we're going to think of the elements as we go through the periods, the different rows. Each period is going to be a different shell. Okay, so Gilbert and Lewis devised this method while he was teaching college chemistry in 1902. So we're going to draw the electron dot structures and the configurations for the first 10 elements. Okay, and we're going to use this layout of the elements here in a bit. And it looks like I need to push this over. All right, so hydrogen. You're going to want to grab a periodic table here, and we're going to look at hydrogen. So if you don't have a periodic table, grab one. I'm going to just be flipping back and forth. Okay, hydrogen. We have one electron here. So whoops, that is not what I want to do. So if I go to my hotel analogy, and this is going to be a lot of scrolling back and forth, so I apologize. Our lowest spot to put that electron is right here in this 1s thing. Now, by convention, we really don't know if that electron is an upspin or a downspin. But by convention, we always start with the upspin. So that one electron is in the 1s orbital, and we have one electron. So we're going to call that 1s1. This is the energy level, the type of orbital, and how many electrons we have. Okay? So energy level, type of orbital, and number of electrons in the sub-level. Okay? So when we do this, we are going to have 1s1, our orbital diagram. Now this is where we actually do the up arrows and down arrows. So we're going to have 1s. We're just going to have one electron up. Now we draw electrons as kind of half arrows. So this would be an up electron or a positive spin, and this would be a down electron or a down spin. Now notice we really just do kind of half arrows. Now the loose dot structure, we only do the electrons with the outermost electrons. So these are the electrons in the valence shell. Which means the electrons in the n equals highest energy level. Okay, so our n here, our highest energy level is 1. We have 1 electron there. So we're going to put the symbol here. We're going to start with just 1 electron. And we're going to do that with a little dot. So we're going to use whatever element we have, and we're going to put dots around those elements to show the various orbitals. Okay? Now, in terms of the quantum number, our energy level was 1 of that electron that we just put in. It was in an s orbital. So remember, s means L is 0. If I put it in a p orbital, that means L is 1. If I put it in a d orbital, that means L is 2. And if I put it in an f orbital, that means L equals 3. So it was an s orbital. So I'm going to put 0. And the orientation, there's only one orientation for n with L. M can only be 0 there. And it was an upspin. So it's going to be positive 1/2. Okay? And let's do helium. Now I should probably do a copy of this instead of scrolling back and forth. Maybe, maybe not. So if I look at helium, I've got 2 electrons here, right? So notice I'm still in that first energy level. Okay? So let's look at my hotel analogy. Oops, that's not what I want. So in my hotel analogy, this is my lowest electron level. It's not full because remember I can put 2 electrons in each of these orbitals. So I'm going to put a downspin in here. Hey!
You ready to try and update that?
Yep.